Hello everyone, Assalamu alaikum. My name is Abrar. In this short lecture, we will talk about full bridge rectifiers. So what are rectifiers? These are electronic devices that can convert our AC signal to the DC. So why do we need that? Because most of our electronic devices are powered by DC source. So at first, let's review what we know about diodes. So diodes are the PN junction that is sandwiched together in a way that can be used as a voltage controlled switch. Diode can operate in two modes. We call them forward bias and the reverse bias. In the forward bias, the positive terminal of the voltage is connected to the positive terminal of our device. In this case, the diode acts as a closed switch, so meaning that it allows current to flow through it. On the other hand, if we connect the positive terminal with the negative side of our diode, this is called the reverse bias, and in this configuration the diode acts as an open switch, meaning it will not let current go through it. So this is what we're going to use in our circuit to electronically control the switching behavior. So now we will talk about our full bridge rectifier or the bridge rectifier. So on the left hand side you can see this is our AC signal, where this is called the positive half cycle and this is the negative half cycle. And the positive half cycle, the AC source will try to push current in this direction, and the negative half cycle, the current will be pushed in this direction. But in our load, our goal is to make a circuit such that our load will experience current only in one direction, say in this one. So how can we accomplish that? Let's divide our problem into two steps. In the positive half cycle, the current is being pushed in this direction, and we want the load to get current in this direction. So we can simply connect this point to this point and this point to this point. So, but connecting them using a simple wire will not be useful, because we want this to be connected only in the first half cycle. So if we recall how our diodes behaved, we want here two diodes in such a way that these two wires are connected in the positive half and open in the negative half. So we can accomplish that by placing two diodes like this. If you see, in the positive half cycle, our AC signal tries to push current in this direction through both of the diodes. So both of the diodes are in forward bias, so the current will be able to go through in this path. But in the negative half cycle, the source will try to push current in this direction, but since it's reverse biased, so the diodes will act as an open circuit and no current will go in this direction. Now, how can we use the negative half cycle then? In the negative half cycle, our AC source will try to push current in this way. So in order to get current in this direction, we can see that we can by simply adding this point to this point and this point to this point. But so we're going to place diode in such a way that in the negative half cycle both of them are in forward bias, and in the positive half cycle they must be in reverse bias, so that there is no connection in the forward case. So this is our circuit. So now in the positive half cycle these two diodes are on, so the current can easily flow in this path. Whereas in the negative half cycle these two diodes will be on, so the current will flow in this direction. So regardless of the current in the source terminals we get from our source, our load will experience current from one direction only. This is our rectification. So now if we place a voltmeter across our load, if we place a voltmeter like that, what are we going to measure? We will see something like this. All the half cycles in the input side will be rectified in our output. Now, this is a DC signal, but this is not a very good one. There are lots of ripples. Then how can we quantify a DC source being better than the other? There are lots of parameters. We are gonna focus on only one of them today. This is the DC component of our signal. The DC component of our signal can be easily measured by taking the average of our signal. So if we see that our signal is periodic after t by 2, where t is the period of our original signal, this is our t, or the period of our input AC signal. So we can simply take the average 0.63 Vm. So let's remember this because we're going to need to compare it later. Now, how can we improve our circuit or make it even flatter than it is? One simple improvement is connect the load with the extra capacitor. Now, what does the capacitor do? In the first quarter of our circuit, in this part, the capacitor will be charged with our input source. But when the input starts to fall, the capacitor won't be able to keep up with it because the capacitor resists the sudden change of voltage. So when the input voltage starts to drop here, the capacitor and the resistor together will form an RC circuit. And if you can recall, the voltage of an RC circuit drops exponentially. RC is the time constant. So you can see that instead of falling like this, it's falling now exponentially. But how long will it fall like this? Till the input voltages. When the input voltage again crosses the capacitor voltage here at this point, the capacitor will start to charge again. So this is the period where the capacitor was being discharged, and this is the period the capacitor is being charged. Since we have introduced a new device or capacitor, we need to know how the output waveform varies with the change of the capacitor. Now if we look at it, we can see that when for a small capacitor, let's say C1, the discharging is much faster than a larger capacitor. Another interesting thing is that for a small capacitor, this was the discharging period. And for a larger capacitor, this is the discharging period. So discharging period increases as the capacitance increases. This is an approximation we're going to use to make some quantitative prediction. Now, let's say this is our 0 point. Let's draw it again so that's clear. Say this is our 0 point. Our input has started to drop, but our voltage due to capacitor, it will keep on decreasing in a much slower rate, and it will do so till this moment. So how can we measure that? As we've seen, as we increase the capacitor value, the drop will be much slower than before. So let's say that we have made the capacitor large enough that discharging period is much larger than the small charging window. Now why is it important? Then this is the half cycle. This is the T by 2 time. So we can approximately say that the discharging takes the whole half cycle. So then we can, since we know the equation, which is, we have already seen that this is the equation, so we can put the T by 2 over here. By placing T by 2 over here, we find the lowest voltage is Vt by 2, which is this. Vm is a minus T by 2 RC. Now, since T is more, since RC is, we have made the capacitor much larger, we can make a Taylor approximation and find this linear equation is equal to Vm is equal to Vm times 1 minus T by 2 RC. Now if we draw our voltage again, there's an observation to make. This was our initial one, this is the better one, improved one. So this is the voltage at this point. What is the voltage here? This is the peak. So at this point the voltage is Vm. Alright, so since we know the maximum and minimum, by taking the average we can find the approximate DC voltage that goes somewhere in the middle. So we can say that we can approximate DC signal by these two signals. And if we do that, this is what we get for our DC. This is our DC signal. Now, if we take RC capacitor value such that the RC value is 2.5 times larger than the period of our AC signal, Then we find the VDC by plugging this in this equation. We find that the VDC is 0.9 VM. Previously, what we got was 0.63 VM. So this is much better than what we have got previously. So this was our short presentation on the rectifier. Thank you.